6.7 features of graphs, making our way through derivatives and through calculus. We're going to apply derivatives and the concept of derivatives to graph functions, okay? So now that we've practiced how to find derivatives of all these different types of functions, now we're going to take everything and apply it to actually graphing functions. This will be beneficial for a non-calculator type of question, because now we're going to use the derivatives to graph functions. We're going to use them to determine intervals of increasing and decreasing. We're going to use them to find maximums and minimums, a whole bunch of different things that, of course, if we had a calculator, we just type in a function to find out, but we can use them without. So f of x is increasing on an interval from a to b when f prime of x is greater than 0. So when the first derivative is greater than 0, without even looking at what the function is, like this actual graph, we'll know that f is increasing on that particular interval from a to b. And vice versa. If the first derivative is less than 0, then we know the function is decreasing. And we know that because, remember, the first derivative talks about the gradients of the tangent lines. And as you can see in this picture, that's what those green lines represent, okay? On the left side, you have a green line that has a positive gradient. And as you can see, if we read from left to right, the graph is increasing. Then on the right-hand side, we have that green line that's going down, so it's a negative gradient. Again, tangent lines, derivative. The derivative is the slope of the tangent line. It's negative, so that means that the graph is decreasing. It is decreasing. We can use sine diagrams, which I'll sometimes refer to as number lines, to determine intervals of where it's increasing and decreasing, okay? Do realize at that very top point, the graph is neither increasing nor decreasing. What is the slope of the tangent line at that particular point? It's equal to 0, okay? It's equal to 0. When the first derivative is equal to 0, this means we have a stationary point. Now there's two different types of stationary points that we can have. We can either have ones that are local maximums and minimums. As we can see in this picture, we have two stationary points. We have two lines in which the first derivative is going to be equal to 0, or in other words, the gradient of the tangent line is 0. And like I said, we have a maximum and minimum at those respective values. They are called local maximums and minimums because that is where we go from increasing to decreasing or decreasing to increasing. Global maximums and minimums, which is another term that can be used, those are like the absolute highest or absolute lowest point on the graph of the function. Okay, so both of these, B and C, those will be local because there's other points along the graph that are higher or lower than those respective points. Okay, so do be aware of that. Do be aware of that terminology, global versus local. Now, sometimes when you set the first derivative equal to 0, it doesn't have like an actual defined maximum or actual defined minimum. In those cases, those are called stationary inflection points, okay? Inflection points. Again, this occurs when there's no maximum or minimum, but it's still where the first derivative is going to equal 0. This usually occurs on these types of functions, which you guys can see. Anybody remember what this type of function is called? X to the third, yes. A lot of your cubic functions, your more basic cubic functions, will have stationary inflection points instead of actual maximums and minimums. So when we have a stationary point, again, that's when the first derivative is equal to 0. We can either have a local maximum, a local minimum, global as well, just kind of depends on the function. Or we could have a stationary inflection point. The Sine diagram or the number line essentially would look like this. And of course, you guys already know we're going to do examples of this. But basically, you have some x value that you determine by setting your first derivative equal to 0. You put that value on the number line. And then what you want to do is you want to test the values to the left and the right of that respective x value. You plug it into the derivative. And you want to determine, are those values positive or negative? Because if the values on the left side of that x are positive, and then on the right side that x are negative, it creates a maximum. Because remember, in the derivative, we're talking about the gradients of the tangent lines. So if those values are positive, that means that all of your gradients are going up, aka increasing, and then negative means they're going down, so it creates a maximum point. Minimum is the opposite. If you go from decreasing to increasing or negative to positive, you have a minimum at that respective a value. Again, a represents some x value that you get when you set the first derivative equal to 0. Stationary inflection points occur when there is no change on both of those. So it goes positive, positive, or negative, negative. Still, that a value occurred when you set the first derivative equal to 0. So it still holds to the whole stationary point concept, but it's not a max or a min. It's actually an inflection point. Okay, and if you notice, these types of curves change from being one way to being another way, like downwards and up, or vice versa. So we're going to use this information to do some examples. We're going to find the intervals where the following functions are increasing and decreasing. Okay? Start you off a little on the lower side of things. Okay? And of course, the only way this would get more complicated is the type of function that you're given. Okay? So f of x equals negative x to the third plus 3x squared plus 5. You're trying to find intervals where the functions are increasing or decreasing. Remember, increasing is when the first derivative is what? What'd you say? Positive. So it's greater than 0. And then decreasing is where the first derivative is negative or less than 0. In order to determine this, we need to figure out where the first derivative is neither increasing nor decreasing. So we got to set it equal to 0. What's the first derivative here? So we find the first derivative, we set it equal to 0, and now we solve it. All of these are not calculated today. No need to have a calculator, okay? So how do I solve this algebraically? I could do the quadratic formula, but I don't have that type of time.
Or you could factor.
I can factor. How do I start? I can take out an x. Anything else? A 3. Okay. So if I take out a 3x, what am I left with?
3x times negative x squared plus 2.
Not negative x squared, but just a negative x, then plus 2. So then I'll set both of those factors equal to 0. And I see that x will equal 0, and x will equal positive 2. Now, these are the values where it's stationary, okay? And there's a possibility that I could have a maximum or a minimum at those values. So this is where you can create a sign diagram or a number line, and you put those respective values on your number line. Then you want to pick test points. These test points are values that are basically in those areas. So then that way we can figure out exactly what intervals this function is increasing or decreasing. What's a value that's less than 0? -1. What's a value that's in between 0 and 2? What's a value that's greater than 2? 3. You plug each of those blue values into your first derivative. Because again, where the first derivative is positive is going to be where it's increasing, and negative is going to be where it's decreasing. So if I plug -1 into the first derivative, and I'm not concerned about the number. I could care less about the number. I'm more concerned about the sign. When I plug in -1, does it give me a positive number or a negative number? Sure? When I plug in -1 into the derivative, it's going to be negative, because you'll end up with the -3 minus 6. What happens when I plug in a +1? Positive. What happens when I plug in 3?
Negative.
Because you'll have
Negative 27 plus 18.
So there'll be a negative. And again, where the first derivative is greater than 0 is where it's increasing, less than 0 is where it's decreasing. So for A, our function is increasing from what to what? From 0 to 2. Remember, we use parentheses here. 1, because at 0 and at 2 is neither increasing nor decreasing. And on top of that, we don't have any endpoints. So we never would include a bracket at any time we're talking about intervals increasing and decreasing. But it's decreasing in 2 different places. From what to what? -infinity to 0. 2 to positive infinity. How do I connect these 2 intervals? A little louder. With the union. Very good. And you can also use your knowledge of like polynomial functions to kind of help you here. This is a cubic that's negative. Negative cubics look like this. So that's why we have decreasing, increasing, then decreasing. Use that to kind of help you graph as well.
If you recognize that, would you still have to do
The
the sign?
sign diagram? No, not necessarily.
Will there ever be situations on the test where they like give us points for our sign diagram?
Where they give you points for the sign diagram? Yes. The question was, is it possible they'll give us points for the sign diagram? Yes, because I mean, you know, with IB, you know, you got A, B, C, D, E, whatever, whatever. Now there might be a part where they ask you to find f prime of a value. That might be helpful for writing the equation of a tangent line, but it's also at the same time telling you whether it's increasing or decreasing based off of if it's positive or negative. So it's a possibility that they can give you that, so then you won't even have to plug it in yourself. I want you guys to try B on your own. The intervals where it's increasing or decreasing.
12x to the third minus 24x squared equals 0.
You can factor out what's it called? 12x.
Just the 12x?
Well,
When I do that, what do I have?
x minus 2.
Keep going. Is it different? Alicia, solve this out for me.
When you do the sine line thing, you put in 0 and 2.
So that's what I got when I saw the back up here?
Yes.
Okay. We do need to put both of those numbers on our number line. Real quick, I forgot to mention this. These right here, when you find those, these are called critical points. Okay, these are called critical points. I want to make sure to highlight that, especially when we did that, did there. So when we set the first order to equal to 0, when we find those values, yes, they are called stationary points. You know, they help us find intervals, but they're also called critical points. Okay. All right. So we make our number line. Now what do I do?
Plug in test points to see if your slope is increasing or decreasing.
Wonderful. Which test points did you use, Zach?
1, -1, and 3.
All right. Pretty similar to the ones from before because we had the same values there. What were my signs going from left to right?
Negative, negative, positive.
Negative, negative, positive. So the graph has something interesting happening here. When it's negative, negative, that means that there's not like an extrema there. It's not a max or a min. It's a what?
Inflection.
It's an inflection point. So what are my intervals of increasing and decreasing? Online. What about increasing? From what to what?
2 to infinity.
Parentheses around both. But what about decreasing? But what about decreasing? So we are decreasing from negative infinity to 2. Even though at this particular point, the first derivative does equal 0. Because there's nothing at 0 that's causing it to change from decreasing to something else. Not a maximum, not a minimum, not an asymptote or any other type of break in that domain, the function is still decreasing from negative infinity to 2. Questions? The reason why I bring that up is because of this. You do have to be aware of asymptotes and other things that make your function undefined. Those are the points that are going to cause your function to have breaks in them, for things to be split up. So if there's no asymptote, if there's no hole, if there's no point of discontinuity, see what I did there? Then it's going to be continuously decreasing from a certain interval to another interval. So, like I said, you need to be aware of asymptotes and other things that make the function undefined on the domain. Those values also need to go on our sign diagram. Okay? So for example, like this one, we have to find intervals where f of x equals 1 over x is increasing or decreasing. If you recall from when we went over functions, what does this look like? It's a rational function.
It's like a little.
Yeah, we have an asymptote of x equals 0 and y equals 0. Okay? So since there is an asymptote here, that asymptote value is going to go on our number line, along with any other critical points that we get when we set the first derivative equal to 0. Okay? So what is our first derivative here?
No.
Oh, no, yeah.
No.
It'd be -1 over
Negative 1 over x to the second power.
the square.
When I set that equal to 0, what happens?
Oh, you lose the x.
Lose the x. So in this case, there are no critical points. Well, no critical points that we can find when the first derivative is equal to 0, but we technically do have something on our number line, and that is the asymptote. So we need to plug our values, our test points, into the derivative. When I plug in a -1 and a +1 into the derivative, which is right here, is that positive or negative? When I plug in 1, is that positive or negative?
Oh,
It's negative. And remember, I drew a little sketch of what the graph looked like, so we knew it should be increasing or decreasing.
Oh.
Is it increasing or decreasing? From what to what? And we need to break this one up because at 0, what's happening again?
It's discontinuous.
It's discontinuous there. And so it breaks up the domain. We can only look at it from the left side of 0 and then from the right side of 0. So do be aware of that. Polynomial functions, they're continuous everywhere unless we got like a hole somewhere randomly. But we wouldn't know that based off of a function. It would have to be like a piecewise function, a graph, or something like that. I want you guys to do this one on your own. Find the stationary points.
Critical
I
point.
meant to say -2, -1. I looked at my paper and I was so tired, I just said 3.
All right. So let's take a look at this. First off, did you try to factor the bottom?
No.
You should, because remember,
Oh.
there's holes, asymptotes, things that can also go in your number line. We want to make sure that they're there. So this would be x plus 3, x minus 1. So we actually have no holes here, but we do have some, what? Asymptotes. Where are they located? -3 and +1. So we have asymptotes there at these respective values. But let's see if there are any other like critical points where there might be a max or a min, okay? Stationary points. So derivative, low, d high. Was it at the top? Minus high, d low. What's the derivative of my bottom? So this will give me 2x squared plus 4x minus 6. Over here, I'll have 4x squared. Then I'll have a -2x. Then I'll have a -6. But since there's a negative out there, I'll need to distribute it over. Is that what you guys got?
Combine the terms.
6's cancel out?
Yeah, the 6 cancel. Yeah.
Okay, just want to make sure.
Yeah, I was looking for that. 0.
Because if I factor out a -2 from the top, that gives me an x minus 3, and still nothing cancels out, so that's cool. So then when I say this equal to 0 to find the critical points, this is just ends up being the numerator equal to 0. I'm gonna take out a -2x instead of just a regular 2x, make it a little easier for myself. So you get x equals 0 and x equals a +3. So I got a few things on here. I got 0 and I got 3 along with the -3 and +1. I still need to do my test points. And I plug my test points into the what? Plug into the derivative. -4, -2, 1/2, 2, 4. These are some values that I could plug in here. And again, I'm not concerned about the number. I'm concerned about the sign. Concerned about the sign. When I plug anything into the denominator, it's going to end up being positive because it's being squared, right? So I'm more concerned just about the numerator, okay? When I plug in -4, that'll give me a -32 minus 24. So this is going to be a negative. When I plug in a -2, this is going to give me a -8 minus 12, which is going to give me another negative. When I plug in 1/2 though, 1/2 squared is 1/4. 1/4 times -2 is a -1/2. 1/2 of 6 is 3. So that's going to give me a positive number. When I plug in 2, it's going to give me -8 plus 12, which is going to be positive. Then when I plug in 4, it's going to give me a -32 plus 24, which is a negative. Now remember, -3 and +1, those were asymptotes. So even though I go negative and then negative in between, on either side of that -3, there's an asymptote, there's a break. So I can't consider that. But at 0, I go from negative to positive. So there's a That's one of my stationary points. It's actually one of my minimums. But at 1, again, I go positive, positive, but there's an asymptote there. At 3, I go positive to negative. What's occurring at 3, a max or a min? A max. So yes, 0 and 3, those are the x values of my stationary points. But I need to actually find their y values. What do? Plug it into the original. When I plug in 0, that'll give me -3 over -3, which equals 1. Then when I plug in 3, that becomes 3 over 12, which is 1/4. And those are my stationary points. Can you visually see it? You have 2 asymptotes. I'm decreasing to increasing, getting close to the asymptotes, never crossing or touching, then increasing to decreasing. All right. I'm gonna skip this one for right now. Let's do this one though instead. Let's put it all together. Let's put it all together before we move forward. So you want to find the derivative. So when you find the derivative, it should be -6x squared plus 12x plus 18. Then you have to draw a sine diagram. So that's your derivative. So from here, what you need to do is you need to set the derivative equal to 0. I'm going to go ahead and factor out a -6. So then that way, when I factor it, it'll be a little bit easier to do. So then this becomes -6, x minus 3, x plus 1. So then my critical points are a +3 and a -1. Now, because this is a polynomial function, there are no asymptotes, there are no holes, there are no breaks, there are no gaps. It's a continuous function from -infinity to +infinity. So my sine diagram is going to have a -1 on it, a +3, and I'm going to use the test points of 0, -2, and +4. Those get plugged into the derivative, so that way I can see if it's going to be positive or negative, increasing or decreasing, which will help me answer the next question. At 0, it is positive. At -2, it is negative. And at 4, it is negative. So because of that, I am going to be increasing from -1 to 3, and then decreasing in 2 different places, -infinity to -1, as well as 3 to infinity. I need to classify and find my stationary points. Well, remember those critical points that I found of -1 and +3, because I go from positive to negative and then, because I go negative to positive and then positive to negative, I have a minimum at -1, and then I have a maximum at 3. Because again, because my sine diagram, my number line goes negative to positive, that's decreasing to increasing, and then increasing to decreasing, which make your max and your min. I had to find the y-coordinate by plugging these into the original function. When I plug -1 into the original function, I get 2 plus 6, which is 8, minus 18, which is -10, -17. And then when I plug 3 in, I'll get -54 plus 54 plus 54 again, minus 7. So then that's going to be 47. Those are going to be my stationary points. Then part D says describe our end behavior. Okay, remember we're talking about limits, so it's basically saying as x approaches to infinity of our respective function, which is g of x, not f of x, our graph is going to be what? Where's it approaching? -infinity. So as x approaches it's going to be approaching infinity. And then the limit as x approaches -infinity of our function, that's going to be approaching what? Negative infinity. And we know this because look at the ends. I'm decreasing after -3. Decreasing means I'm going down. So as x is getting bigger, I'm going down. As x is going closer to negative infinity, it's decreasing, but it's coming from a higher value at the end. I have to use all this information to basically sketch this graph using the features that I found. Well, I found a maximum at -1, -17. I'm sorry, minimum at -1, -17. And then there's a maximum at 347. I should be decreasing, then increasing, then decreasing. And there's a sketch of my graph, making sure I hit those few things. I can even include a y-intercept. What's my y-intercept? Plug 0 into the original. There we go. I can also use remainder theorem if I wanted to find the zeros, but it's a sketch, not a draw. Don't forget about those things as well. All right. The last little bit that we're going to talk about today, I put the sign because my answer was here, yes. All right. Last thing we're going to talk about today is, save that one for later. Is concavity. This is the last little bit of notes because everything else is examples from here. That's what the second derivative tells us. It tells us the shape or the curvature of the graph. If the second derivative is less than 0, then it's concave down. If the first derivative is greater than 0, then it's concave up. And that's what it means by being concave down and concave up. If the second derivative equals 0 and there's a sign change, in other words, it changes concavity, then that respective point is an inflection point. Not a stationary inflection point, but like a legit inflection point, okay? It's a non-stationary inflection point because at that respective point, the first derivative does not equal 0. All right? Wait.
No, concavity sounds like a better word.
Mm-hmm. Because remember, our stationary inflection points were the ones that went like this, okay? But non-stationary means that that tangent line, like it's not, the gradient is not going to equal 0 in those cases. So then it's just a regular inflection point. But if that first derivative does equal 0 and the second derivative equals 0 at that point, then it's a stationary inflection point.
Okay, so it goes from down to up.
Correct. And that's what, like this one over here, x to the third, that's what it is, because it's concave down until 0, and then it switches and it's concave up. Okay, but that's an example of a stationary inflection point because at that point, the first derivative also equals 0 at that x value.
And if it's, so what's going on in that graph down there?
So in this graph, this is showing a non-stationary inflection point, which is just called an inflection point.
Okay.
This is when the second derivative is equal to 0. It changed from being concave up to concave down or vice versa. But the gradient of the tangent line is not equal to 0.
So it's technically something because it's changing, but it's not changing like.
Right. That one, these are true inflection points. All right. And so we'll talk about it some more on Thursday. We're going to continue to do more practice. I'm going to see if I can find some more challenging problems, and we're going to continue to graph functions. But to summarize everything that we talked about, the first derivative helps us determine extrema, maximums and minimums, increasing, decreasing intervals, and the second derivative helps us determine concavity. And literally all you do to find the second derivative is it's the derivative of the derivative, okay? And you set it equal to 0, the second derivative, to determine if you have an inflection point. And then you can test it the same way we tested for maximums and minimums. All right?